So where I am at the moment is trying to give you an understanding of how light-emitting diodes work. And light-emitting diodes are finally, they're diodes, they're electronic devices. And so I need to build up to how a light-emitting diode works. I really have to go through how electronic devices work, modern electronics, the world of semiconductor electronics. So this is that story. And I'm going to actually, as background, I'm going to take a step back to looking at how atoms work again. We've already talked about a little bit about atoms, and I want to sort of flesh out a few more details. Some of the stuff you've seen in K through 12, particularly in chemistry, they talk about the orbitals of atoms and the s orbitals, the d orbitals, p orbitals, and all that, and they kind of pull them. In my memory of that experience myself, which is a bit back there, was it was just pulled out of a hat. You know, rabbit after rabbit came out of a hat. And so I'm hoping that to give you a little bit more real understanding of what an atom's like, and we'll use that to build into the story of semiconductor devices and in electronics. So I told you that, you know, one of the great discoveries of the previous century was that electrons in atoms are not little planets. They are little standing waves. And if they were little planets, they could orbit the nucleus at any distance they liked from the nucleus, arbitrarily closely spaced distances. And so there would be no energetic structure to an atom. An atom could have any energy it wanted to, or I should say the electron in an atom could have any energy it wanted to up to the point where it leaves. So you just make the orbit bigger, it's got a little more energy. You can make it bigger still, it's got a little more energy and all that. There'd be no structure to the whole thing. If you imagine assembling the simplest of atoms, a hydrogen atom, it's just a little positively charged proton sitting there. You bring in an electron, it pulls that electron toward it, so it does work on you, and you could get it, you need to put a little bit of energy into the motion of this to make it orbit. But you could pick any energy you like, and you could find an orbit that would work. In fact, that's not the way the world works, our universe works. The electrons in atoms go into standing waves, and they're very limited. Well, they're certainly much more limited than pure, simple mechanical orbits, classical orbits. The standing waves, you can only have certain standing waves living around that nucleus. I should say electron standing waves living around that positively charged nucleus. They've got to fit the right number of wavelengths in, otherwise they're chaotic. So you put them in and they fit right, you've got an orbital. You put them in and they fit right, another orbital, and so on. And there are not that many choices for the standing waves that are in snug close to the nucleus. As you get farther out, there's more opportunity to move around. You can get more orbitals. And in fact, ultimately, the number of orbitals is in principle infinite. But that involves orbitals that are hugely far from the nucleus and are never seen. So the point then is, when you're building an atom, hydrogen's the simplest of choices. You can put the electron in the innermost orbital, the one closest to the nucleus, and it has it releases the most energy in going in and getting close. And that's the ground state orbital for a hydrogen atom. For a neon atom, which I talked about with the neon lamp, there are 10 electrons to come into that, to join that positively charged nucleus and produce a neutral object. And so as you imagine bringing in the electrons to the nucleus has 10 fundamental positive charges. So you bring in 10 electrons. The first one goes into the orbital that has the least energy, that does the most work on you in coming on in. The electron sits there. That's actually quite a lot of energy to get in there. It's hard to get that electron off, that last electron, because it sees a positively charged nucleus with 10 positive fundamental charges. Anyway, it's in there. You bring another electron in. It goes into the same standing wave, but it's now interacting with the other electron and noticing, well, there's a negatively charged guy here already, which is not so attractive to me because I'm negatively charged. And so the energy of the second electron is not, doesn't release as much energy in coming in and landing and becoming part of the orbital. And you work your way up, 3 electrons, 4 electrons, 5, and that 10th electron as you're bringing them in, they're more and more interacting with each other. The electrons are not oblivious to one another, and that changes the orbital structure somewhat. So to make sure I'm painting this picture clearly, the orbitals that you learn mostly in chemistry are what are called the hydrogenic orbitals. The orbitals where there's only one electron. And life is simple because the one electron notices only that positively charged nucleus, and there's nothing else around. But as you begin to build the more complicated atoms with several electrons, they are talking to each other, and they're pushing each other apart in many respects. And that changes the orbital structure subtly. And is this important? It creates sort of the richness of the structure of atoms. They're all really, they're patterns, but there are differences between them because of those interactions between electrons. Another feature of this orbital arrangement, as you bring in the electrons, the orbitals, each one has an energy associated with it, and this is sort of physics. It's partly sort of physics convention and jargon and all that, to think there's an energy associated with an orbital. What really that's talking about is that if you put an electron in that orbital, the energy released in the process will be a certain amount. So each orbital has associated an energy, the energy released in bringing the electron in. And it turns out that there's structure to that, to the energy of the orbitals as you bring in more and more electrons. They're not evenly spaced in energy, I guess I should say. So you don't bring in one and it releases 10 units. The first electron, 10 units of energy. Second one, 9. Third one, 8 and 7. It's much more complicated structure than that. And it has to do with how the standing waves fit around that nucleus and the structure of those standing waves. And they're not trivial in structure. You've seen them in chemistry. They have weird shapes, some of them, like the dumbbell shapes of the p orbitals, I don't even know how to describe them, shapes of the d orbitals and so on. They're complicated. The bottom line of this then is there are times when you're adding an electron and it takes dramatically more, it releases dramatically less energy than the last electron you put in. So you bring one in, it releases a lot of energy, you bring another, it releases a moderate amount of energy and so on. And then you bring maybe the last one in, and I'll pick an atom, sodium. The last electron, when you bring it into sodium, the sodium atom only barely grabs onto it, and it goes into a much higher energy orbital. And the consequence of that is that electron is kind of loosely attached. In sodium, it is loosely attached. The last electron that goes into sodium is in chemistry, we would describe it as one electron beyond a closed shell. And the shell structure is sort of a concept that there are times when you put an electron in and it goes in and gets bound strongly in there, and the next electron that would come in would not be strongly bound. So you filled some sort of shell, and the next electron would just go in a much higher energy orbital, be much more loosely attached. Where I'm going then with this is neon is actually a closed shell atom, meaning that the last electron that goes into neon to finish it, to make it electrically neutral, is quite strongly bound. A lot of energy is released. That's more jargon. It's so easy to use jargon in this, and hopefully you can see, at least get some idea of what I'm saying when I'm using it. But that electron is strongly bound, meaning lots of energy is released in the act of pulling it in. And if you were to bring in another electron, it doesn't want another electron because it's already electrically neutral. But if you were to bring another one in, the next available orbital is way up in energy, and would be much more weakly attached. So you have sort of filled a special grouping, and it doesn't really want another electron for reasons having to do with its orbits, not because of electric charge. But just the orbits it's happy. You finished a set of orbitals. And just for your own information, there's a whole series of gases on the right side of the periodic chart, which you've surely seen at some point or other. They're known as the noble gases, and they are gases in which that last electron, the one that came in to make them electrically neutral, filled a shell, was tightly bound, but the next electron would be not tightly bound, and the atom just doesn't care much about it. The consequence of that is that having the shell full, like in neon, and the other ones are familiar to you as helium, argon, krypton, neon, xenon. I always said neon, of course. And then there's a radioactive one that you run into at your, radon, not a good, Radon's around. It's mostly a nuisance because it's radioactive, but it's a rare gas. Anyhow, that right side of the periodic chart, those atoms, they're gaseous for good reason, because not only are the last electrons not tightly bound, but in order to coax one of those electrons into a higher orbital, it takes a lot of energy. You can do it. The electric discharge does it. But other contexts, it's hard to coax it into an orbital with higher energy because the next step is a big one. The next available orbital is way up in energy. Questions about this? I'm just barreling along here. The result is that those atoms have trouble interacting with other atoms, for example, polarizing. To shift their charges around, they need to start using some of the other orbitals, but they're so far out of reach in energy that they can't use them. So the atom's kind of like a hard, closed ball. It doesn't want to deal with anything, including other electric charges and other atoms. It just ignores most of them to a large extent. And as a result, they're very aloof. They wander around as gas particles. You have to turn these into liquids, you have to go pretty cold to liquefy the so-called noble gases. All right? Any questions in general about atoms? I don't really need to teach a whole course on how atoms work, but I won't do that. I'm going to use some of those tools to talk about how solids work. So atoms, I told you the quantum standing waves in atoms are structured around that positively charged nucleus, and so they have an orbital character to them. They're called orbits. But the electrons in a solid, an extended solid, and most solids, I should tell you, are crystalline, whether you know that or not. I mean, you've seen a lot of solids that are crystalline, like a piece of quartz or a diamond or a ruby. But even the ones that aren't obviously crystalline are crystalline. I mean, certainly salt you can tell is crystalline. Sugar is crystalline. All the metals are crystalline with rare exception. It's hard to make a non-crystalline metal. You don't see the facets and stuff in the metals, but believe it or not, they're crystalline. What does it mean to be crystalline? It means that if you zoom in close, look at the atoms, so you're really looking through a microscope, you start seeing the atoms, they're going to be in orderly arrangements. The way if you go to a grocery store and you look at the displays of fruit, if they've been really picky and they have all the oranges the same size and stuff, they'll often will stack them in some nice orderly array. And with a crystalline, you have a behavior that if you look at a small part of the crystal, or in the grocery store, you look at a small collection of fruit, from their arrangement, you can predict where you will find another atom in the crystal or another fruit in the display. This local area tells you a lot about how things are going to be going off into the distance. So that makes them, that's a common in crystals. All right? So if you imagine assembling a crystalline solid, so yay, it's got atoms in it. But let's tear the atoms apart first and put just the nuclei, and we'll put them in the places that they're supposed to end up. Because you can start with a crystal and then we're going to deconstruct it. Pull all the electrons out. Leave the nuclei in place. They hate this, of course, because they're all positively charged. They would love to move now, but we won't let them. And we now begin to bring in electrons. Where do they go? Well, the nuclei, what I'm going to do is I'm trying to decide whether I want to go a particular, add a complexity, but I'll leave it aside. When you bring the electrons in, they do have to decide, are they going to live around one nucleus or are they going to live in the collection of nuclei, that first electron? And as the aside that I don't want to go to, I will tell you it and then I will walk away from it, is that the most tightly bound of the electrons really will find a nucleus that they will spend most of their time around. They are so strongly attached to it that they go around that and they don't care about the other nuclei very much. But let's not worry about those first few electrons. Maybe we're partway into the story already of building a solid, and there will come a time when you bring in the electrons, and they won't be so committed to one nucleus. They will agree to be shared by the nuclei, and what their goal in life is to be in the lowest energy standing wave they can be in, and that turns out to be distributed across the material. It comes as close as it can, the wave does, the strength of the wave comes as close as it can to all the positively charged nuclei, so that's good. That reduces electrostatic potential energy. And the wave also has crests that are as widely spread, as big wavelengths as it can get. And I told you several times now that the kinetic energy of the electron is associated with the spacing between crests, the wavelength. So it can minimize its energy by finding a wave that's close to the nuclei and that has big wavelengths. And it will spread out across the entire solid, in principle at least. It will be a standing wave of the whole solid, in much the same way that I showed you with the vibrating spring. We had a standing wave across the entire spring. It was dancing in place. Sometimes, I managed to get the fundamental, which is this motion of the spring, and I got three extreme points, what are called antinodes. Actually, I got four. I got 3 nodes, 4 antinodes. It doesn't matter. The details of that don't matter. But basically, those standing waves extend across the entire solid in principle. In practice, there's often something that interrupts the story and it sort of subdivides the world. But let's imagine we're working with the whole solid. So where this goes then is that when you build the solid back, you put all the electrons in, they go sequentially into the lowest energy standing waves of the entire material, what are called levels. Why call them levels? Well, it's in honor of the fact that each one has a certain level of energy. Orbital is not the right word for them anymore because they're not orbiting anything. They're living in a box, essentially a box that is the material. And you begin to fill up the levels from approximately the lowest energy one on up. In the absence of thermal energy, you certainly would go from lowest energy and up. Thermal energy makes life a little more complicated, but we don't need to worry much about it. And you keep adding electrons to this material to reconstruct it until you've brought it to electrical neutrality. And you will have put 2 electrons in every level, again, because you can have a spin-up electron and a spin-down electron, and that distinguishes the 2 of them. They're now allowed to coexist in the same standing wave. All right, so that's how you build a solid in concept. Any questions about that so far? One of the crucial issues is what's life like, or what are the characteristics of the levels when you finally put the last few electrons in? What are the levels like that the electrons went into, and what are the levels like that additional electrons would go into if you had to put more in, if you hadn't basically run out of electrons, didn't need any more? That determines a lot of characteristics of the material. It does that in part because, just like with atoms, remember atoms, the orbitals in atoms have sort of they're structured in energy. They're not uniformly spaced in energy. Sometimes you have orbitals that have very similar energies, meaning the electrons in those standing waves would have same energy. You can move in fact, you can move from one orbital to the other. You can shift the electron from this orbital to that orbital with almost no investment or removal of energy. The same energy, who cares? You can have it on this side or that side, big deal. There are other times in atoms where moving an electron from this orbital to the only other available orbitals means moving them way up in energy. Like in neon, if you want to move an electron out of its current orbital in neon, you can't move it in any other low energy orbital because they're full. They have electrons in them already. So your only opportunity is to move it from one of the levels orbitals it's in, to a much higher energy orbital. A process involves investing a lot of energy. So neon just doesn't like this at all. You can move electrons to another orbital, but you have to pay for it big time. The same thing happens with solids. As you're assembling the solid and you're putting electrons in, you put them in certain groups of standing waves, and then you finish that group of standing waves, and then there's another group of standing waves that are different in character somewhat. Kind of like the s orbitals versus the p orbitals versus the d orbitals versus the 1s versus 2s, all the things that you may have learned in chemistry. There's structure to the levels in a solid. And they they have groups of energies that are similar. And those are often they're given a name, they're called a band of levels. Just not a surprising name. There are similar, they're bands of orbitals. Well, they're shells of orbitals. It's a similar idea that the orbitals in a solid typically show up in bands that have similar character in the structure of the standing wave and also similar energies. So as you're filling up you're building out and rebuilding the solid, putting electrons in, you fill bands of levels, and you start filling the next band of levels, then you start filling the next band of levels. They're all working their way up in energy, and eventually you run out of electrons. And one of the key issues is, did you fill a band at the same time that you put the last electron in? If you did, you created an insulator. Okay, which is the question that, I didn't go back to tell you what the question I'm addressing right now is, but why is an insulator an insulator? The reason an insulator is an insulator is that in order to build it, as you put the electrons in, you run out of electrons at the same time you run out of levels in a band. And if you were to put the next electron in, it would go into a level in a different band that would release far less energy. The electron would be much less happy in this new level. The consequence of that is that if you go back to get rid of this extra electron, just look at the electrons you got. If you want to get those electrons, one of the electrons to shift into a new level, an empty level, it's got to be empty, right? Because all the other levels nearby are in energy. And here too, if I get confusing when I talk about nearby, and it's nearby not in space, like here and here, but nearby in energy, meaning you got the low energy guy and you got those really high energy guy. Anyway, I use the word nearby as for different worlds of nearness. So we're turning to this. If you got a solid, you filled all the electrons in the bands, you filled all the levels in the bands with electrons. If you try to get those electrons to rearrange, they can't do it. Not without a big investment of energy. Why? Because all the levels with similar energies are full, and the Pauli exclusion principle forbids you from piling extras in. And if you want to take an electron out of a certain orbital, and I view these orbitals as like placeholders, boxes, and I've got them up there as boxes. If you want to take an electron out of one of these boxes that is a certain standing wave and shift it into another standing wave, you look around, all the standing waves with similar energies are occupied. Somebody else is there. So you got to look for an unoccupied level. And I'm looking up because I'm thinking up in energy. You got to find them, and there's not one here, there's one here. Big energy difference. And getting there, who's going to pay for that? So all the electrons are kind of stuck in their current standing waves. They can't do anything. They're just stuck there. And that's similar to how neon or one of the other noble gases, the electrons in those atoms are stuck. You can't get them to do much. They don't form chemical they don't get involved in chemical reactions because the electrons are kind of stuck. And here, these electrons don't get involved in things like moving because they're kind of stuck. And that makes an insulator. And let me see, this is an insulator. Just to flip ahead. The way I think about, my analogy, I should say. My analogy to an insulator and this idea of filling the levels is, it's a theater analogy. So if you read it, great. If not, I'll tell it to you again, that if you got a theater like this, and every single seat is full, meaning that you have put an electron in every level in the ground floor of the theater. We're not going to pay attention yet to the balconies and stuff. Maybe, yeah. So every seat's full, and I say, okay, everybody move west, right? It's going to be tough to do that because you've got no empty seats to move into. You're sort of boxed in, and we can worry about whether you can rip the people off the left side, the west side of the chairs and put new people in from the right. That's a little bit fuzzy, and a fuzzy part of my analogy, but basically a theater that's completely full, every seat's full, is very hard for people to move. Is that okay? And that you end up with a material that does not conduct electricity in the real world version of this. If you have all the electrons filling a band of levels, so you have a completely full band at the lower energy part of the story, a band that gets a conventional name. It's called the valence band. And if you remember the idea of a valence in chemistry, it's the same word. So the valence it's the band, it's the most highest energy band that has electrons in it. It's not empty. The conduction band is a name for the band of levels that is empty. It's a set of standing waves, in other words, levels, that electrons could be in, but they're not. And in my theater analogy, that's the balcony. So suppose there's an empty balcony. The ground floor is completely full with people. The balcony is completely empty with people. I tell people to move west, and no one can do it. The people on the ground floor can't move because they're boxed in. The people in the balcony, which is the analogy of the conduction band, well, there are no people there, so they can't move left either, west either. All right? So insulators occur when the material, when it assembles such that the electrons fill the valence band, no empties, and they leave the conduction band empty. And there is an energy, what's called an energy gap, or a band gap, between those two bands of levels. And what that just means is that it would take energy to move, a significant energy, I should say, to move an electron from one of the valence band levels, in other words, the ground floor, analogous to the ground floor of the theater, to the empty conduction levels, the balcony. It would take a lot of energy to do that. And as long as nobody is willing to provide that energy, nothing's going to go through this. I'm going back and forth between the analogy and the real world. In the theater, nobody can move. In the solid, no charge can move. Therefore, you can't get current to flow through this thing. If you put high voltage at one end, low voltage at the other, you get an electric field in the material, and electrons would go, I want to go opposite the field. They're negatively charged. They want to go opposite the field, but they're boxed in. They can't move. So they just sit there. And so that's diamond, that's salt, that's glass, that's plastics, all these insulating materials. They're in this situation. You've filled the valence band and left the conduction band empty. Any questions about this? The real one or the analogy. So that's an insulator. That makes it an insulator. What's an alternative? Suppose you run out of electrons while you're building the material. And again, this is a hypothetical or conceptual process. When you're building material, you put in electrons, and you run out of electrons, meaning you've reached electrical neutrality, but you were in the middle of filling a band of levels, maybe halfway through. And so the next electron you would put in would go into a level that was almost indistinguishable in energy from the one you just filled with the last electron. In that case, you got a conductor. Why? Because you have partially filled that band. It's very easy, that is, it takes tiny energy for an electron to move from whatever standing wave it's in, whatever its level it's in, to one of the levels that's not being used. And so if you put an electric field on this, by putting high voltage to one side, low voltage to the other, there's an electric field pointing, and the electrons will go opposite that. They are happy. They can do this because they can move with tiny energy. They can shift around. With energy actually provided by the electric field, they can shift around between standing waves and make progress across the material. And the analogy here is like, again, a theater. We won't worry about the balcony right now, but the ground floor is not full. it's sparse, not sparse, we don't know, it doesn't matter whether it's sparse or almost full, somewhere in that territory. And now if I say everybody move west, you can do it because you can find a seat nearby to hop over and then another seat to hop over. Everybody can start hopping. And in the book animations that I created, you actually, I try to make it so you actually can see electrons hopping. They just keep moving. The hopping is a little bit cartoonish. The actual physical mechanisms in which they move is more complicated, but it's still this quantum. It's a quantum evolution of the waves working their way across, but they do work. They move, and so you end up with a conductor. So all the metals that you've encountered fit this bill. The electrons, as they're going in there, when they finally fill you run out of electrons, they have partially filled bands. And it is energetically very easy for the electrons to shift into new standing waves and therefore make progress across the material. Just to put in a name of something that's part of the world of semiconductor or solid state physics, there's a convention of calling, identifying the energy associated with the last filled orbital level. The last electron you put in had a certain energy. The next electron that you would put in if you needed to would have a certain energy. They're different. They're always a little bit different. If you take the average of their energies, 50-50, right in between them, that's called the Fermi level. It's just a concept. It just tells you the energy. It is specifically, it's the energy halfway in between the last filled level and the next level you would fill. It's useful to know where that Fermi level is. Why? Because if the Fermi level is in the middle of a band, as it is here, I've pointed to it, it's right there. It's drawn as a horizontal line in my drawings and common like that. This is a weird drawing, and I should have told you long ago. This is space left to right, but it's energy vertically. So this is a level on the left side of the material, but it is at low energy because it's down low. This is still in the same location more or less, but it's at higher energy and so on. Here's a similar level on the right side of the material. I mean, hopefully you were able to get this by looking at it, but maybe or maybe not. Anyway, the point is the Fermi level is a level in energy, not in space. It just tells you that here's where all the action is. There's an electron just below this in energy, and the next electron you put in would be just above this in energy. Is that okay? Just to name it, Fermi level. The Fermi level in a metal occurs in the middle of somewhere in a band, and because you haven't finished filling. In contrast, the Fermi level in an insulator occurs between bands. Right? We've filled all these levels down here in this band of levels, the so-called valence band, and we have not yet filled any of the levels. There are no electrons in these standing waves of the conduction band, and the Fermi level is in between. And the fact that it's in the between with a huge energy desert above it and below it means that this isn't going to conduct any electricity. All right? Any questions about insulators and metals? Believe it or not, we're still going towards how a diode and ultimately light emitting diode works. That's the goal here. Okay, so a semiconductor. How does charge move in a semiconductor? I hope you still hear the word semiconductor in common use. All the electronics, so everything is being built in Silicon Valley. Silicon. What's silicon? Silicon is an element in its pure form, and they can make it remarkably pure. Silicon is it's an insulator, meaning that you fill the last electron, of course, goes in and fills a band. But it's something of a. It's not a weak insulator. It doesn't take all that much energy to move an electron out of the highest energy valence levels into the lowest energy conduction levels. The energy distance between those those two isn't so big. A strong insulator, a good insulator, would be something like salt. Actually, is pretty good. Quartz is pretty good. It takes a lot of energy to move an electron from the valence band to the conduction band. Not so much in silicon. So silicon has become the workhorse for electronics, most electronics, and silicon is technically an insulator, but you can get it to start conducting electricity in two ways, one more interesting than the other. One way is to heat the stuff. Hot silicon has extra energy in it, and there is often enough energy in hot silicon. I don't know how hot is hot, you put it in the oven. There's enough energy around thermally to toss electrons up into the conduction levels. That's not what this drawing is showing you, but I'll tell you that's an important effect, and that is one of the reasons why you don't want your electronics to overheat. If it overheats, the silicon stops being what it's supposed to be, namely an insulating type thing, and it becomes more of a conducting like metal thing because it's got electrons up there in the conduction band that can move, and that's a problem, and it misbehaves and often destroys itself. So semiconductor devices work best to keep the temperature under control. So that's the public service announcement piece. This, what I'm drawing here, is what happens when silicon is exposed to light. And if you look, silicon, before we send in light, let me go back. There's silicon, for example, before we send in light, we'll keep it cold. And all the electrons in the valence band, all electrons have filled the valence band and the bands below it. They're out of sight here. And there's nothing in the conduction band, no current can flow through this. But if you expose it to light, something happens. The light comes along, and remember light, although it's a wave, travels as waves, it's absorbed and emitted as photons, as little packets of energy. If one of these little packets of energy comes along and has enough energy to move the electron from this level, namely this standing wave, in the valence band, to this level, a different standing wave in the conduction band, the electron shifts. The photon energy did it. And now that electron being up there in the conduction band, the balcony of my theater, it can move in response to an electric field. So you put an electric field on it and off it goes. And similarly, you've created an empty seat in the ground floor of my theater, and now it provides the opportunity for things to move. So with the exposure to light, silicon becomes a conductor. Depends on how much light. A little light, you get a little conductor. A lot of light, you get a lot of conductor. It's a photoconductor. And we talked about photoconductors. I talked about photoconductors back in the days of Xerox machines. Remember that Xerox copiers, how those worked? And I said, oh, we'll eventually circle back to how a photoconductor works. This is how a photoconductor works. They apply a coating on that drum that is an insulator in the dark and in the cold. Because all the electrons have piled into the valence band and below and filled it. And the conduction band's empty. But you expose it to light, now the electrons can move from valence levels to conduction levels, and now they can move. Questions? This is back to xerographic copier. So light can turn these guys into conductors. All right. Okay, so still going towards light-emitting diodes. Now, I've given you enough background on what an insulator is, a conductor is, and a semiconductor is it's an insulator with a small energy gap between the valence band and conduction band. You okay with that? Code of silence goes on. All right. What if you start mucking around with the silicon? So I do have silicon in mind when I'm talking about this, but there are other semiconductors, some of which are important and in common use. But we can stick with silicon's good enough. If you take silicon and you remove a couple of atoms from the overall solid and you replace them with atoms that have, well, fewer electrons. For example, to the left of silicon in the periodic chart is aluminum. The aluminum atom is very similar to silicon, except It has one fewer proton on its nucleus, and therefore it attracts one fewer electron. So if you put that in to the silicon crystal, it'll go in. Aluminum, you can put aluminum into a silicon crystal, and the crystal will still form, and it will be almost happy, but not quite. It's a little bit like, who brought these guys in here? We didn't invite them. Okay, so there they are. And it means as you're filling in the electrons to build this hypothetical solid again, you run out of electrons earlier than before. There just aren't that many electrons because the aluminums didn't bring in their fair share. And as a result, you get the same band structure for all practical purposes, but some of the electrons are missing in the valence band. So this material now it's given a name. It's called P for positive, P-type semiconductor. It's a material very much like normal semiconductor, normal silicon specifically, but it's got a few empty levels in it, depending on how much you contaminated the silicon. That contamination process is called doping, and it predates sports doping. Okay, but it's the same idea. Okay, so you put in some aluminum into the silicon, and you end up with empty levels in the valence band, and everything else is pretty much similar. Well, that means this is an electrical conductor, and the more aluminum you put into it, the more you empty out the valence levels, the better a conductor it becomes. Okay, so you can make silicon that conducts electricity a little bit by putting doping it with aluminum. So it's called N-type semiconductor. P-type semiconductor for positive. All right? Any questions about P-type semiconductor? Okay, to silicon's right is I'm sure it's phosphorus. Phosphorus is to the right of silicon. It has one additional proton on its nucleus, and therefore attracts one additional electron in. If you dope silicon with phosphorus, you put a little bit of that in there, those phosphorus atoms bring in extra electrons, and you run out of valence band levels before you run out of electrons, because the phosphorus brought in more than their fair share. You got to put them somewhere. They got to go into some standing wave. They go into the conduction levels, and so they're partly filling that balcony. And so phosphorus doped semiconductor is also an electrical conductor, depending on how much you put in there. And the result is that it's given another name. It conducts. It's called N-type semiconductor because it's negative. I'll give you the story behind why it's called P-type versus N-type. The N-type is easy. When you put extra electrons up there in the conduction level and you apply an electric field, those little negatively charged electrons move. So what's moving through the material is truly a negatively charged thingy. Okay? So the current is traveling through this material by way of these negative charges moving along. So we'll call it N-type material because it's negative type things carrying the charge, carrying the current. Is that okay? What does that say for P-type semiconductor? Well, the weird thing about P-type semiconductor is that what facilitates the moving charge is not so much the electrons. Yeah, they do move ultimately, but the empty spots. Wherever you've got an empty spot, you can move an electron into it, which leaves another empty spot, which you can move another electron into. And what's kind of moving through the material is the empty spot. Like imagine this room was almost full of people, a couple of empty spots. And you can only move one seat at a time. If we watch that happen, we watch the empty spot will be there, and then a person will move. Then the empty spot will be there and move. The empty spot will be moving across the room. Is that okay? The empty spot has a character of not a negative charge, but a positive charge. It moves with the field. The electrons go the other way. This bubbly empty spot moves the other way. So it has a positive character. It's called P-type. Is that okay? The official name for it is a hole. So P-type semiconductors move charge by way of holes. The holes move through the material, the empty levels. Okay? if nothing else, that might help you remember the names. Anyway, P-type semiconductor, N-type, they both conduct electricity depending on how much they are doped. By themselves, they're kind of boring. Why don't you just use a metal? But what if you touch the two of them together? All right, this is just the story that I'm going to touch them. So there they are, sitting there, minding their own business, my usual statement. You'll notice I got them. I'm thinking of them as spatially separated by a very small distance. Two chunks. This really is on the left side. This really is on the right side. Vertical is energy still, so it doesn't tell you anything about space. But there's a spatial gap between those two. And this material, this N-type material, has electrons up here in the conduction level where they have a fair amount of energy per electron. They would prefer not to be there because that's extra energy. They would love these electrons right here in my anthropomorphized world. Look across that empty gap and go, ooh, if we could only get over there into that P-type semiconductor and we could shift into lower energy standing waves and give up energy, and that would be great, yay. Can we do that? No, there's a gap between us. But if we touch, poof, they touched. And this is not how diodes are made. They don't actually make two materials and touch them. They build them together. But you could do this in principle. You make the two materials and touch them. When you touch them, the charges do migrate. The electrons in the conduction levels near the junction, this is called the PN junction, P and N, because you're bringing together P and N semiconductors. The electrons near the junction do migrate across it, and they leave the conduction levels and enter the valence levels of the other side. So they leave the conduction levels of the N-type semiconductor and enter the valence levels of the P-type semiconductor, a process that releases energy. And they will continue to do this until they have built up a significant electric field in this middle part. As they cross, as negative charges leave the right and end up on the left side develops a net negative charge, and the right side a net positive charge, so there's an electric field there. It's like a little charge, it's like a little capacitor. And that building up of charge eventually stops the migration, because eventually these electrons, for example, it's going to take too much energy to take them out of this side, which is positively charged, and add them to this side, which is negatively charged. There's a repulsion that just says, no, you can't go. So the migration stops, and when it has, look at this central region. It has all the conduction levels are full, valence levels are full, and all the conduction levels are empty by virtue of this migration and settling. And this is called the depletion region. It's an insulator again. It doesn't carry electric current. That PN junction loses its ability to conduct electricity right there in that central region. Time goes by so fast. You can get charges to move through this by applying an electric field externally, but only in one direction. So, golly, it's too, you can only get the charges. I'll come back to this property, but I'm going to give you the short bit. You can get charges to flow across this system in one direction. You have to push the electrons in from the N-type semiconductor side and take them out of the P-type semiconductor side. That allows them to migrate across the junction again. You're undoing the electric field that built up that tried to stop them. And when they drop, they go in here. Once they get across the junction and make the step from up here to down here, there's a step in energy. They're shifting from one quantum wave to another. In a conventional diode, they create heat because their energy is released. In a light-emitting diode, the whole point of the story, they emit light. So what you're seeing in these light-emitting diodes is electrons pushed in on the N-type semiconductor side, migrating across the junction, and then shifting from a conduction level to a valence level and emitting light in the process. And if that isn't bright enough for you, this is more fun. Ready, get set. I probably should not electrocute myself here. That's a pretty good bang for an object this small, isn't it? Ooh. Yeah, it's basically a street light on a handheld street light.